Alright, this is already the last of the presentations on the general differentiation rules, because there are only 3 general differentiation rules that involve general functions, namely the product rule, the quotient rule, and the chain rule, which is discussed in this presentation. All other differentiation rules that we'll discuss will talk about specific functions or specific families of functions, such as trigonometric functions, for example. The other thing that I want to say about this presentation is this one is going to roll up all the ideas, all the conceptual things that we've discussed in Calculus one more time. We'll talk about graphing as well as optimization, which means if you're on top of this section, you can pretty much say you understand a substantial chunk of multivariable calculus. So in some ways, this is a first capstone, if you will. Now let's get to it and let's talk about the chain rule. The question that the chain rule answers is what the derivative of a composition is. Now let's remind ourselves first of all what a composition does. Basically, functions can be envisioned as black boxes that take input and produce output. And so if x goes into the function k, then the function k converts that into the output k of x goes out. And the composition then is basically that output goes into another function as input, and that function will produce an output to the function. The next function now can't be called g also, so k also, so we call it g, and that converts the input k of x into output g of k of x, and that's what's coming out on the other side. So it is something that can and does happen quite frequently also in application. You've got one process that produces something, and that is put into another process. That's basically what compositions do. And now the question is, how do those things differentiate? We've seen from the product and the quotient rules that the derivative may not be obvious. We're not going to go through a proof here. We're going to go through a motivation that is based on a kinematic visualization of the derivative. Namely, let's just draw ourselves some axes and think about what happens when you travel along a straight line. Suppose you're at x and you are moving, and then of course your y coordinate is y, and suppose you take s steps to the right in the x direction. Well, then you have a horizontal speed s in the x direction. Well, that would be the distance traveled in one time unit, right? Speed is distance traveled per time, and the number itself is the distance that you travel per time unit, whatever your time units may be. So you go from x to x plus s, and that would mean that in the y direction, you go from y not to y plus s, but to y plus ms, right? Because if you remember the slope formula being a rise over run, for a run of 1, you get a rise of m, which means for a run of s, you could get a rise of m times s. And that means that the slope, if we're thinking of this s as a speed, then the slope is actually a multiplicative factor that turns horizontal speed into vertical speed. Now, the slope of a straight line is the derivative of a straight line. So if we go at a certain speed in the x direction, then the speed in the y direction is the derivative times the horizontal speed, and that's what we're going to talk about on the next slide. Okay, so the vertical speed is m, or m times s. Okay, so now how does this work for a function? Well, for a function f, we may be at a point x, and then of course your y coordinate is f of x. If we go at a speed s in the x direction, that would be now horizontal instantaneous speed, because of course things will change as we travel along the function for the vertical speed. But the horizontal instantaneous speed, that will ultimately give us the distance traveled on the tangent in one time unit. So on the tangent, or overall, we would go from x to x plus s, and instantaneously at this stage that looks to the particle that is traveling along this function as if we're going on this tangent from x to x plus s. And that would mean we would end up at f of x plus f prime of x times s. And so the vertical instantaneous speed, if we're looking at a horizontal instantaneous speed of 1, would be f prime of x. So again, the derivative is a multiplicative factor for the speed, and it's turning horizontal speed into vertical speed. Okay, so now let's look at what happens with a composition. We start with a function k, and we're moving with speed 1 in the x direction. then because instantaneous speed always just considers tangent lines, that means the slope of the tangent, which is k prime of x, translates the speed 1 in the x direction into a speed k prime of x in the k direction. And of course, the output of k becomes the input of g in a composition, and position and speed are preserved. So now this position here becomes this position on the x-axis, or on the k-axis, if you will, and the speed is now k prime in the k direction, and we remember that the derivative just multiplies that speed, and so the derivative, the slope at k of x, is g prime of k of x, and the vertical speed now is the slope that we have multiplied by the horizontal speed, so the speed in the g direction, and the output direction is g prime of k of x times k prime of x. And so just as the derivative of a single function takes a speed 1 and turns it into a speed k prime of x, if we're looking at a composition, the composition takes an original horizontal speed 1 and turns it into a speed g prime of k of x times k prime of x. Now this one takes a while to get used to. Think about it for a little bit, but the upshot ultimately is that the derivative of a composition is given by the chain rule. And so if a function is g composed with k, where g is differentiable at k of x and k is differentiable at x, then the derivative g composed with k prime of x is g prime of k of x times k prime of x, or verbally, the derivative of a composition of functions is the derivative of the outer function evaluated at the inner function. That's this part right here, up to here, well, including the parentheses, times the derivative of the inner function, which is this k prime of x here. Okay, let's see this thing in action. If we want to compute the derivative of a function e to the x squared plus 1, let's say, well, the derivative would be the derivative of the outer function, which is the exponential function, and the derivative of the exponential function is just e to the x, so we get e with the inner function plugged in, so we get e to the x squared plus 1 times the derivative of the inner function, which is 2x. And interestingly enough, that's already it. There's nothing we can do to simplify here. So that is a fairly quick problem, which is certainly nice. We can now use the chain rule to compute all sorts of things that we couldn't compute before. For example, we can compute the tangent line of the function f of x equals 1 over 1 plus x to the fourth at x equals 1. Yes, you could use the quotient rule here, and if you do that correctly, I don't think there is anything where anybody could say you've done anything wrong. But using the quotient rule is smiled at a little bit by some mathematicians because, well, you have a derivative of 0 and all that. So another way to do this is to use the chain rule and to realize that the function f of x, which is 1 over 1 plus x to the fourth, is just 1 plus x to the fourth to the minus 1. And then with the chain rule, we get that the derivative is negative 1 times 1 plus x to the fourth to the negative 2, right? The derivative of anything to the minus 1 is negative 1 times the anything to the negative 2, and the anything is this. And then we have to still take the derivative of the inside, which is 4x cubed. And so that ends up giving us that the derivative is negative 4x cubed over 1 plus x to the fourth quantity squared. And now we're interested in the tangent line at x equals 1, so we plug in 1. We should end up with negative 1 here, right? Negative, f of, not f prime. We have f of 1 first, and f of 1 is 1/2. Yes, sure, because that's 1 over 1 plus 1. Whoa, I was just seeing something wrong here. We also need f prime of 1, and f prime of 1 ought to be negative 1, right? Because you get 4 divided by 2 squared. Goodness gracious, thank you. My arithmetic is still working. That is a relief. And then, well, we know that y is equal to mx plus b. Y is 1/2, m is negative 1, x is 1, and b is the one that we want to find out. And so that gives us that b is equal to 3/2, and the tangent line is y equals negative x plus 3/2. And as we know, we can always double check by just graphing the function, finding the point, and graphing the proposed tangent line. And yes, that really is the tangent line here. In this picture, it looks as if the tangent line actually cuts through the function, and I think that is the case. But if you zoom in on this area, you realize that the straight line really looks tangential under high magnification, and that's always the verification that we've gotten the right kind of tangent, that we've gotten the right line for the tangent line. Okay, we can also find where a function is increasing or decreasing, and here's where this part that I've mentioned also in the product and quotient representation sneaks itself back in, and that is that we have to use these differentiation rules in conjunction, right? Products are the most easily overlooked parts, because a product, well, this thing doesn't scream at us, hey, I am a product, even though it is. And the next most easily overlooked part then is differentiation of the exponential, especially when it's easy, because the derivative of e to the negative x is minus e to the negative x, because the minus comes from the derivative of the exponent there. So let's first find the derivative here. With the product rule, we need the derivative of the first factor, and the derivative of e to anything is just e to the anything, times the derivative of the exponent, which is that -1 that I've talked about, times the derivative of the second factor, which is x, times the second factor itself, which is x minus 1 quantity squared. And then we have plus the first factor times the derivative of the second factor, which will be 2 times whatever is inside to the first, which we don't have to write down, times the derivative of the inside, which is 1, so we don't have to worry about that. And, well, what does that give us? That's already, I factor out an x minus 1, sure. Factor out e to the minus x times x minus 1. That's common to the first factor and the second factor. And what remains then is a negative x minus 1 from the first summand and a 2 from the second summand. And that gives us overall then that this is e to the negative x times x minus 1 times 3 minus x. Yeah, that's what that is. And, well, if you don't see that factorization, you would want to use the quadratic formula to get the zeros. It works in the same fashion you've seen here. I certainly tangled up my tongue as I tried to do that. I ultimately got it right because, of course, these slides are pre-made. If you feel like you're doing something where you tangle yourself up, you stop doing that right now and just take it step by step. Write another line, write another 2 lines, write another 3 or 5 lines. I don't care. The important thing is you want to get it right. And here, well, thankfully, we have gotten this right. And so now we set this equal to 0. We find the critical points, which are 1 and 3. Remember, the exponential function doesn't have any zeros. And then we do our number line. We have 2 critical points, 1 and 3. We need to use checkpoints, 3 of them, in the places as indicated. To the left of 1, we have 0. Between 1 and 3, we've got 2. To the right of 3, we've got 4. Notice that the scale isn't quite right here, but hey, we're going to get the double check real well. Then we plug 0 into f prime, and let's see, f prime is right here. So let's see, the exponential is always positive, 0 minus 1 is negative, and 3 minus 0 is positive, so f prime should be negative. At 2, the exponential is positive, 2 minus 1 is positive, 3 minus 2 is positive, so at 2, the derivative ought to be positive, and at 4, the exponential is positive, 4 minus 1 is positive, 3 minus 4 is negative, so the derivative should be negative, which means our function is decreasing, increasing, and decreasing. And again, we can also compare that with a calculator plot. And when we do that, we see that with our critical points being at 1 and at 3, and the checkpoints here actually also almost scaling. I'm slightly impressed here, but I mean, it compares pretty well, and we can see that the function is first decreasing, then increasing, and then decreasing. So the graphics and the analytic stuff certainly need to be consistent with each other, and they are here. Well, now we're coming to a lengthy example. I've already talked about graphing by hand being a good exercise in the structured processing of information, as well as if there is a mistake, which there won't be on this slide, it would be good training in troubleshooting. And then also, as you do this on paper, it trains manual dexterity as well as visual thinking also. So there's a good bit of stuff in graphing, despite the fact that we have graphing calculators and computers who could plot this thing here very quickly. So let's go through the graphing procedure. Typically, I suggest to go in a certain order, and the first thing I suggest to do is to determine the growth behavior, where the function is increasing or decreasing. And so for that, we need f prime. And f prime is derivative of the numerator, 3x squared, times the denominator, 4 minus x squared, minus the derivative of the denominator, negative 2x, times the numerator x cubed divided by 4 minus x squared squared. That's just the quotient rule. We will ultimately use the chain rule as we compute the second derivative, where we need the derivative of the denominator, and I'll talk about that when we get to it. Here, well, it's algebra. It's going to take a while. It may be a little bit tedious, but remember, it's just algebra. We can do it, and that's the most important thing. So I'd say we just multiply out the parentheses here, right? Yeah, and I already combined some stuff. Let's see, how does this go? We get 3x squared times 4, that's 12x squared, that's good. Then we get negative 3x to the fourth minus negative 2x to the fourth. So that would be negative 3x to the fourth plus 2x to the fourth, that's just minus x to the fourth. And the denominator stays the same. Okay, so here I think I'm also pressed for space. I've talked about that in the other presentation too, so I squeezed things together a little bit. If you need an extra step, you just write it down. If you need an extra step in a book, you need to write that extra step in the margin. Critical points for this thing are the zeros of the numerator. So you set the numerator equal to 0, and here we can, let's see, we can factor out an x squared. And so that's x squared times 12 minus x squared, and that means that the critical points are x equals 0 and x equals plus minus root 12, so minus root 12 and root 12. And if we're setting the denominator equal to 0, 4 minus x squared equals 0 gives us critical points negative 2 and 2. So this time we've got 5 critical points, so we need a number line with 5 critical points. Things are going to get a little bit squeezed. What I always would tell you is use a full extra sheet of paper for your graph and your collection of information. And then just make the graph as large as possible. I'm certainly squeezed here because of size of the panel as well as font size, so it's going to be a little bit crunched up, but that's just unavoidable here. You'll have more room, and I want you to use that room. So let's see. Root 12 is less than root 16, so it's less than 4, but it's certainly more than root 4. So the leftmost one should be negative root 12, then comes negative 2, then comes 0, then comes 2, then comes root 12, and we'll need checkpoints in all the areas. Something to the left of negative root 12 is negative 4, something between negative root 12 and negative 2 is negative 3, negative 1 is between negative 2 and 0, 1 is between 0 and 2, 3 is between 2 and root 12, and 4 is to the right of root 12. And then we have to plug that into the derivative. Oh goodness, let's see. Again, we can weasel out of dealing with the denominator because the denominator is non-negative everywhere, and then as long as we're not plugging in negative 2 and 2, and we don't, it's in fact always positive, so we only have to worry about the numerator. And let's see, negative 4 squared is 16, so we end up with 12 times 16 minus, and negative 4 to the fourth is 16 times 16. Well, 12 times 16 minus 16 times 16, that's negative, so the derivative is negative here. Plug in negative 3, we get 9 times 12, minus 9 times 9. Well, that ought to be positive, and it is. Plug in negative 1, we get 12 minus 1, that's still positive. Plug in 1, we get 12 minus 1, that's positive. Plug in 3, we get 12 times 9 minus 9 times 9, that's still positive. And we plug in 4, and we get 12 times 16 minus 16 times 16, and that's negative. Now you see here, with a little bit of number sense, as people call it, with a little bit of practice working with numbers, you can do this fairly quickly and mentally, and you don't have to do the whole computation, because remember, we're only interested in whether this is positive or negative. But also remember how I tangled myself up in one of the earlier examples, and so if you get the feeling that you are tangling up, well then do the computation on a separate piece of paper, or if you have a calculator available, stick it into a calculator. Remember, the important thing is to get this right. That's the most impressive part. Doing something very quickly and with very few steps and wrong, that's not impressive at all. Okay, so this translates into the function being decreasing, increasing, 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 and decreasing on the respective intervals. And that does it for the discussion of the growth behavior. We move on to curvature. We move on to the function, whether the function is concave up or concave down. And for that, we need the second derivative. So let's remind ourselves what the first derivative is. And here's the second derivative. And here's where we will need the chain rule, and where I need to say a few words about what typically happens with these kinds of quotients. So take the derivative, and of course we use the quotient rule also, right? We need the derivative of the numerator, 24x minus 4x cubed, times the denominator, 4 minus x squared, quantity squared, minus derivative of the denominator. And here's where we need the chain rule. 2 times the inside, which is 4 minus x squared to the first, which we don't have to write down, times the derivative of the inside, which is minus 2x. And then we multiply with the numerator, which is 12x squared minus x to the fourth quantity. Make sure you have all the parentheses in there, and then, of course, the denominator. That's another thing when you differentiate a complicated quotient. I've seen it more often than not that people somehow let down their guard and forget to write down the denominator, and that's, of course, not good either. So we have to write down the denominator here, 4 minus x squared, quantity squared squared, which is just a fourth power. And now here's why I typically recommend to not multiply out denominators in these kinds of quotients, and that's because we've got a 4 minus x squared quantity squared in the first summand, and we've got a 4 minus x squared as a factor in the second summand. That means we can cancel 4 minus x squared. And the way I've done that here is I always want us to be better safe than sorry. So first factor out the 4 minus x squared, keep the rest, which is 24x minus 4x cubed, times 4 minus x squared minus 2 times negative 2x times 12x squared minus x to the fourth. And now we see we can cancel the 4 minus x squared against one of the 4 minus x squared in the denominator, 4 minus x squared in the denominator. That gives us an overall denominator of 4 minus x squared quantity cubed. And here is then where I collect the terms rather rapidly, because as you can see, space is a little bit limited. So let's see if we can work out the mental arithmetic that went along with this. Let's see. We have 24x times 4. That's 96x. Yeah, that's right here. We've got 24x times x squared, times negative x squared, which is negative 24x cubed. But we also have let's think about this. Oh yeah, we've got negative 24x cubed, and then we have 4x cubed times 4, which is negative 16 x cubed, so that gives us 24 plus 16, that's negative 40 x cubed. And then we have negative 2 times negative 2, which is 4 times 12, which is 48, times x squared, which is 48x cubed, and 48x cubed minus 40x cubed, that's 8x cubed. And we already have taken care of the x's, and finally we have a 4x cubed, negative 4x cubed, times a negative x squared, which is a 4x to the fifth. And we have a minus 2 times minus 2x times minus x to the fourth. That's a minus 4x to the fifth. So we end up with 4x to the fifth minus 4x to the fifth. And that is gone. And that really does take care of all the terms. And of course, in some ways, I'm allowed to cheat here because I already know what the result is right here, but I really did mentally keep track of all the terms, and they were all there. Now, this is good mental training. This is this kind of brain training that I sometimes, tongue-in-cheek, make a little bit of fun of. Brain training is valuable, and if you can do something like this in your mind, more power to you. A lot of things will become easier if you can do that. If not, remember, don't try to unnecessarily impress yourself or anybody else. Just write it out and then do the cancellations. It's an extra line. I just don't have enough room here. Okay, now we want the critical point, so we have to set the numerator equal to 0. I think we can factor out an 8x here. Yeah, that's 8x times x squared remains from the first one, and 96, and a 12 remains from the second one, because 12 times 8 is 96, with the x coming from the 8x. And that gives us just one possible inflection point, which is x equals 0. And then we have the derivative, the zeros of the denominator, and well, the zeros of x squared minus 4, or 4 minus x squared, are just plus minus 2. So on our number line, we just end up with 3 possible inflection points at negative 2, 0, and 2. That should mean that our checkpoints are negative 3, negative 1, 1, and 3. Choose them as conveniently as possible. And remember that the checkpoints are always plugged into the function that gave us these cut points here. So the checkpoint goes into the second derivative, and this time around, because we've got a third power in the denominator, we also have to deal with the sign of the denominator. So let's take a look at this. We plug in -3, we end up with 4 minus 9, which is negative, and you cube that, and that's negative also. You don't need to know what the number is, you just need to know the denominator is negative. Plug in the -3 in the numerator, you get -3 cubed, which is negative, and you get 96 times a negative number, that's also negative, so you end up with a negative numerator. Negative divided by negative is positive, so you end up with a positive second derivative. Okay, -1 plugged in, 4 minus 1 cubed, that's negative, and you have 8 times the negative number is negative, 96 times the negative number, that's negative also, so you get negative divided by positive this time, so the second derivative should be negative here, and it is. Plug in 1, you get positive divided by positive, so that should be positive. And you plug in 3, you get positive divided by negative, so that should be negative, and it is. Which means the function is concave up, concave down, concave up, concave down in the respective areas. And that does it for curvature. We now take care of a couple of things that are typically algebraic or done with limits, such as the oblique asymptote. And here the function f of x, I tricked around a little bit because, again, I don't have enough room. This is something that you would do with a long division. But x cubed is x times x squared. We know that, sure. And x squared is x squared minus 4 plus 4. And I can work that out now because x times x squared minus 4 divided by 4 minus x squared is minus x. And what remains is the 4x over 4 minus x squared, which goes to 0 as x goes to infinity, which means our oblique asymptote actually is y equals -x. The vertical asymptotes are where the denominator is equal to 0, the potential vertical asymptotes. So you set 0 equal to 4 minus x squared, you end up with x being -2 and +2. And yes, our function will go off to plus or minus infinity there, because at -2 and at +2, our numerator is not 0. Our vertical tangents, well, there are no vertical tangents for this rational function. And our symmetry is that this function, or our symmetry, we typically check whether the function is even or odd. So let's look at f of -x. You just plug in -x and you pull out the negative signs, and you realize -x cubed is negative quantity x cubed. Negative x squared is just x squared, so it changes into negative x cubed divided by 4 minus x squared. And that's just negative x cubed over 4 minus x squared, which is minus f of x, and so that means that the function is odd. And now we can just go ahead and start working out our the behavior of the function. So we have a bunch of regions that our axis is being cut up into, namely one region or one cutting line for every critical point and for every possible inflection point. And within those regions, we see the function is decreasing concave up, increasing concave up, increasing concave down, increasing concave up, increasing concave down, and finally decreasing concave down. Then we can just sketch our number line, which is of course then scaled in accordance with what we get from our critical points and our inflection points. And so we've got a scale here, -3, -4, -3, -2, -1, 1, 2, 3, and 4. Our y-axis is of course cutting through x equals 0. And I don't think we even have much of a scale on the y-axis. Well, yes, we will have a scale on the y-axis because the f of the -√12 will give us something. But the scale ultimately is -8, -6, -4, -2, 2, 4, 6, and 8. And that is inspired from the values of the function at -√12, which I ought to have computed for you somewhere. If not, we'll just do it in our heads, and I'll show you that too. Right now here we're also putting in the vertical asymptote at -2 and at 2. We're putting in the oblique asymptote, which is y equals -1. Note that because the scale on the y-axis is different than the scale on the x-axis, this is not really a diagonal geometrically, even though once you take the scale into account, it really is the diagonal. And now, now we're getting the y-intercept, which is f of 0 equals 0, so that's right here. The x-intercepts, well, x cubed equals 0 gives us x equals 0. values. We need f of negative root 12. Well, that's going to be fun to compute. Negative root 12 cubed divided by 4 minus negative root 12 squared. Well, let's see. Negative root 12 squared is just 12. 4 minus 12 is negative 8. And this guy up here is 12 times root 12 with a negative sign. So the negative signs cancel, and we end up with negative 12 to the 3 halves divided by negative 8. So that ends up being 3 to the 3 halves. 8 is not 4 to the 3 halves. No. None of that really makes sense to me right now. And that's, of course, highly annoying. Pause. Okay, well, what happened is I made a mistake. That doesn't excuse the mistake, but certainly these kinds of things do happen. I fixed it, caught it and we fixed it. That also sometimes happens in class, and actually we're having quite a bit of fun when that happens in a face-to-face class because, well, I mean, sometimes a student just has to tell me, Doc, 4 times 4 is not 36, which it isn't, but let's take a look at what happened here. Okay, so up to here we were okay. Negative 12 to the 3 halves divided by negative 8 will give us something that is positive. 12 to the 3 halves is just 12 times root 12, and 12 over 8 is 3 halves, so this ends up being 12 times 3 halves times root 12. And that is approximately 5.1962, and of course that's where I use the calculator. Similarly, the value of f at root 12 ends up being root 12 cubed over 4 minus root 12 squared, which is 12 to the 3 halves over negative 8. This time the negative sign persists, so we end up with negative 3 halves times root 12, which is approximately negative 5.1962. And those decimals now allow us to put those points in there. The change from decreasing to increasing happens at this point here, and the change, then we've got our x and y intercept, which is 0, 0, and a change from increasing to decreasing happens right here. And well, now we can just draw in the function, and we know that as x goes to infinity, as x goes to minus infinity, the function has to be near its tangent line here. As x approaches negative 2, the function will go either to plus or minus infinity, and the only way the function can blow up and be increasing, as is guaranteed here, is that it goes to plus infinity. Then it'll come back from minus infinity, because you can only increase away from an infinite value if the infinite value is negative infinity. It'll then go to infinity, or minus infinity being increasing, so it's going to go to infinity up here. And it's going to remain increasing, so it's going to come back from negative infinity and then turn around here and then approach its asymptote again. So that means if we work this out, the function comes in like this from somewhere near the asymptote. The picture isn't wide enough to really show how close the function gets to its asymptote. It blows up, it goes to plus infinity here, it comes back from minus infinity, turns around here, and in fact, because we have a horizontal tangent line, because this was a critical point, it comes in horizontally, then it continues to increase and goes off to infinity. It comes back from minus infinity, goes through the turnaround point, through the relative maximum, and then approaches the oblique asymptote again. And again, the really cool thing is, I mean, we've plotted 3 points here. We've done a lot of graphical arguments that just put the various properties together. And if we flash that across, we can see that this picture here is pretty much the picture that I've created with a little bit of software. And again, the picture that we sketched may not be as accurate in terms of plotting points as this computer-generated picture is, but in the computer-generated picture, we would have a really hard time determining that the x-coordinate of this point really is negative root 12 and that it is here root 12. So again, the graphing certainly allows us to predict the shape of a function and to understand the shape of a function without plotting a bunch of points. Because this, I mean, this is, you've got a picture, but why the picture looks the way that it does, well, that's not something that the calculator can tell you. Okay, we're moving on to optimization. And, well, this is obviously a made-up problem. It is inspired by an article that a mathematician once actually wrote that was titled "Do Dogs Know Calculus?" And, well, of course, the upshot is no, dogs don't do calculus. But in this kind of situation, animals as well as humans often just instinctively try to find the optimal path. So what's the situation here? We've got a dog who can run 12 feet per second along a straight beach, and it can swim 3 feet per second in the water. And a ball is thrown into the water, which lands 20 feet offshore, so that the point on the beach that is closest to that spot is 100 feet away from the dog. So that means in order for the dog to get to that ball, the dog could run along the beach and then jump in at the point closest to the ball, or it could jump into the water right away. But of course, the dog could also do any kind of combination of running and jumping a little bit earlier. And so what we want to do is we want to determine the route the dog should run to reach the ball most quickly. This kind of problem can be done to determine fastest routes to go to a certain place. It can also be used to optimize land electricity lines to a house that is way outside of town, where maybe you can lay at a certain price electricity lines along a road, but then it will probably be a bit more expensive to lay the line through or across country. And so this is in some ways a pattern that is replicated in various ways, and this certainly is a made-up problem and it's a toy problem, but it shows how to do the optimization rather well. So what do we do? Well, the first recommendation for any kind of word problem always is that if you can visualize it, draw a picture. So here's a straight beach. Here's where the dog stands at first, presumably with its owner, who throws a ball into the water, and the ball lands somewhere here. The problem tells us that the ball is in the water, and what the dog can do is it could just swim right away, it could run and then swim like this, or it could branch off at a certain point, and that is really what ultimately will happen. And what we're interested in is the optimal branching point, so that we have a combination of straight running and then diagonal swimming to get to the ball. And in order to work that out, well, we're going to say that the branching point is x units or x feet before this point where the vertical line meets the beach. That means that the dog runs for 100 minus x feet, and then because this distance here is 20 feet, it will swim square root of x squared plus 400 quantity in feet. And well, what we're interested in is not the distance. What we're interested in is the time that the dog takes, and we know, and pretty much the only thing I know about velocity is distance over time, and we can solve that for the time, so we end up with the time being distance over velocity, and that means that the time that the dog will take to get from the start to the ball, depending on where the branching point is, depending on what x is, will be 1 over 12, 100 minus x. Yeah, 100 minus x is the distance, and 12 feet per second is the speed of the dog, plus 1 over 3, so 1 over the speed in the water times the distance traveled in the water, square root x squared plus 400. I already pulled the denominators out front as fractions, because in that way they will act like constants and the derivatives will be a bit easier to compute. Okay, so now we have to find the minimum value of this function, because we want to minimize the time. And well, that basically means we have our function from the previous panel, which is 1/12 100 minus x plus 1/3 square root of x squared plus 400. The derivative of that is, well, 1/12 times 100 is just a number. The derivative of that is 0. 1/12 times negative x, the derivative of that is negative 1/12. The 1/3 is just a constant that comes out. And here is another one of those places where the chain rule certainly sneaks in. So let's see, how does that go? The square root is essentially a power 1/2. So we get 1/2 times the inside to the negative 1/2 times the derivative of the inside, which is a 2x. Okay, the 2x and the 1/2 just gives us an x, and the inside was x squared plus 400 raised to the negative 1/2 after we differentiated it, and raising something to the negative 1/2 is like dividing by its square root, so that derivative really ends up being x over square root x squared plus 400. Again, I've combined a few steps. You want to be able to take care of these things mentally. Well, I've tangled my tongue up here, and I've made a mistake here, but remember the mistake that I made here, I caught because I mentally went through the arithmetic one more time. So there is something to be said for doing these things mentally, for being very concentrated. If it doesn't work out, just write down another line, for goodness sakes. It's not that bad, right? Okay, now we have to set the derivative equal to 0. So we end up with 1/12 being equal to this 1/3 x over square root x squared plus 400. We should probably multiply the square root x squared plus 400 over, and I may have pulled the 12 over here. Yeah, we get square root x squared plus 400 equals 4x, because of course the 12 over 3 gives us a 4. We get rid of the square root by squaring everything, so we get x squared plus 400 equals 16x squared. Thank goodness it's all x squared, so that means basically 400 is 15x squared. X squared is 400 over 15. Well, 400 divided by 5 is 80, and 15 divided by 5 is 3. Thank goodness at least some of my mental arithmetic still works. And that means that x12 is plus minus square root 80 over 3. And yes, we use calculators for that. That ends up being plus minus 5.1640. And, well, x is between 0 and 100, right? If we're remembering the picture, a negative branching point would mean that the dog overshoots and then runs back, and that is not sensible, and that's also what a dog typically doesn't do unless the ball changes its position or so. And so now we have to find out which solution is the optimal one, because we also have to take into account the boundaries, x equals 0 and x equals 100. So as a reminder, here's our function. T of 0 is easy to compute. That's just 1/12 times 100 plus 1/3 times square root 400. So it's 100 over 12 plus 20 over 3. Let's see, that would be 25 over 3 plus 20 over 3. So that's 45 over 3. Ha! I can still do some stuff, and I swear I didn't peek during the pause as to what that would be. Well, 45 over 3, that's 15. That was a little bit easier. So the dog would take 15 seconds if it were to use x equals 0, which means it would run all the way along the beach and then go at a right angle turn, go straight into the water. And it's in seconds, of course. T of 100, that would be if the dog were to jump right in and swim all the way. Well, 100 squared is 10,000, so we end up with 1/3 times square root 10,400. That's going to be pretty big. That's 33.9935 seconds. So, and that makes sense. Swimming takes a lot longer than running, so jumping in and swimming is very inefficient. And finally, T of square root 80 over 3. Notice I didn't even pretend anything here. I stuck that straight into the calculator. Ends up being 14.7883 in seconds. So the savings is on the order of 2/10 of a second, which really is not that great. In other kinds of optimization problems of this type, you realize that you may be able to save a couple of $100 laying an electrical line or so, and that really is realistic. Let's get back to this article that a mathematician once wrote about do dogs know calculus? No calculus. I don't know the speed that the dog was running or that the dog could swim, but basically this colleague measured the speed for the swimming and the running, computed the optimum branching point, which is of course this x here, and then just basically played with his dog and measured where the dog would jump into the water, and it turned out that the dog really instinctively was pretty much going into the water around the optimum branching point. No, the dog did not take a piece of paper, figure out the actual optimum branching point, and then jump in, but basically instinctively the animal knew at a certain place it should just jump into the water. Sometimes it overshot a little, sometimes it undershot a little, but it definitely stayed away from the extremes, and the dog definitely tried or was instinctively really jumping into the water near the place where things are accurate. So there's a good bit in terms of physiology and in terms of instinct that does connect with stuff that we can then work out more exactly. Also, that was quite interesting in that article. If you want to look it up, you probably would just want to Google the phrase "do dogs know calculus?" I think the article is publicly available. But in closing here, enough about dogs. What have we seen in terms of calculus? We have seen the chain rule in action. We've seen the chain rule in action in conjunction with the product rule and the quotient rule. we have seen that we can now graph rational functions rather exactly and modulo small mistakes, and I think I'll even leave that mistake in. It's a nice teachable moment. I am self-confident enough to admit that yes, I can and do make mistakes. And we've also seen optimization one more time. So as I may have mentioned earlier, if you're on top of this section, if you're on top of this part of the course, you pretty much understand what you need to understand about single variable calculus. The only extensions that we're going to have now is we're going to introduce more differentiation formulas, such as for trigonometric functions as well as for logarithmic functions. We'll introduce some more applications like related rates. We're going to introduce things like numerical mathematics, Newton's method, and so on. But basically, conceptually as well as close to also symbolically, we pretty much are on top of single variable calculus. That being the case, I think you deserve a break, but after that, let's get back to it. The next thing up are the derivatives of trigonometric functions. I'll see you there.